as a workshop where we can really address what are the challenges and what are the opportunities and this extraordinary family of enzymes that we work with. And so hopefully we'll have a lot of discussion and not just leave the meeting and go home, but have some ways that we might follow through after the meeting. And it's really this structures that we have a lot of structures, and how do we really now look at the dynamics and allostery and really consider the theoretical aspects of how these molecules work. And so what I'd like you to think about is, as we go through all of the talks, are what are the challenges and what are the opportunities. Because I think if we look at where we are now, the ability to do faster and faster simulations, the ability to experimentally validate the simulations, and I think it's really quite an exceptional time, and that maybe we can really pioneer some very new things with this area. So I went through some history, just where we've come over the last couple of decades. And this was our very first experiment with this ATP analog, and we labeled this lysine 72. So that was a long time ago that we did that. And then this other hydrophobic carbodiamide cross-linked carboxyl groups with amino groups. And so this was labeling these two residues. And so that was in 1989, before we had any structures, but we knew then that these were two conserved residues and that they most likely were cross-linked close to the ATP binding site. And so then this is just a history of all the sequencing, and this first paper that Tony Hunter did of comparing all these sequences was in 1988. That was pre-blast. That was, and recognizing from that this was a very large family, and of course now we have all the genomes, and it's one of the largest gene families. And this was the first structure, and a lot of things, I mean, when you saw this and you knew the sequence conservation, you knew that fold was going to be conserved. There's also a phosphate on activation loop here, which you can understand how that organized the molecule. This is an inhibitor. It's an alanine, not a substrate, but it's still a really good model for how proteins fit at the active site. And here's that lysine 72, and here's the ASP184. So that was actually in this, we did a lot of work here at the Supercomputer Center when we first saw this structure, and we had our first workshop in 1989. And over the years, every now and then, we've had workshops here, and it's been a good way to, some of you, a few of you were here at that first one, to try to think broadly about this structure and this family of enzymes. And I think we still have this really good transition state mimic for pKa. And one of the questions I really think about is, why has it been so hard to get substrate transition state-like complexes like this with other kinases? And is pKa really weird that we are able to do that? And so this is now the structure tree, and so we're filling in. So we have a structural kinome, not just the sequence, and so that provides us with real opportunities that we didn't have before. Hoping we can fill this. Stefan Knapp couldn't come today, but we filled in a lot more. These are just some of the structures that have been solved. So I want to try and get a comprehensive set of the structures that have been solved. And so from those that we have solved that the fold is conserved, but what is really unique about each of these kinases are the surfaces. And I think that is a real challenge for us now. Often we have only a core, and SARC we have more than a core now, but if we just look at what are the things that dock to all these different parts of the surface, and often it's not just one thing. It's like when it's active, it's binding to one domain or one protein, and when it's inactive, it's binding to another. So these are very dynamic molecules, but they are scaffolds for protein recognition as well as catalysts. And so if we just look at pKa, what if we had only the core, and it's got these two little tails at each end, but if you look at the core, this is the core only. And if we only have the core of pKa, we wouldn't have an active kinase either. And you can kind of see just how those tails wrap around the core, and they really are an integral part of the functional kinase. And just looking at this C-terminal tail and how this part, which if there's no ligands bound, you don't even see this, you can't trace it. It's very dynamic, and it's an integral part of the ATP binding site. So if you don't have this phenylalanine, that's not an active kinase, and so probably in some cases that's why we really don't have the ATP binding quite right at the active site, because you're missing something. It's not a part of the core. And again, these are scaffolds, not only catalysts, and so just one of the things with pKa, we saw that first structure and the structure of the regulatory subunit, but it's really only when you have the complex, which is fairly recently, that you can understand how it's activated by, how it's inhibited and how it's activated by cyclic AMP. And again, I think I see that as a real challenge of, so this is how cyclic AMP binds, it's a receptor for cyclic AMP, but when you look at the holoenzyme complex, it's really seeing this complex that allowed us to understand how that molecule really works. And you could guess about some things, but you needed a complex. And so I think for all of us as a challenge to try to get complexes of these kinases with their associated domains or other proteins, with their substrates, that's certainly one of the challenges for structural biologists. And then just one other thing I wanted to comment on is that what other opportunities do we have now that we have a lot of structures to compare that we couldn't really do before? And so one of the things that Alexander Cornet has been doing the last couple of years is looking at what elements are conserved in defining these non-linear elements. I don't even know what to call these, so you might have some ideas here, but they're spatially conserved elements that are really characteristic of the kinase family. And this is the first regulatory spine. He called this a spine, where there are these conserved hydrophobic residues that stack up when you have an active kinase. And when you have an inactive kinase, this spine is disrupted. And then if you go and look at all of what is conserved, and these are coming from different parts of this is from the large lobe, from the DFG motif in the activation segment, from the C helix, and from beta strand 4. So they line up, but they're coming from different parts of the molecule. And then if you look at the core, and how do you organize the core, a couple of things have emerged. And one is that there's a very unusual F helix that's very hydrophobic helix that goes right through the middle of the core. It is actually a really defining element. So this is this conserved glutamic acid that's anchored to this regulatory spine. And then you can define what he's called a catalytic spine. And this is unusual in that, again, these are small lobe residues, these are large lobe residues, and the small lobe and the large lobe are coupled by the adenine ring of ATP. So we call this a catalytic spine. And it really engages the small lobe and the large lobe, and then the other thing the small lobe has to do is really position that gamma phosphate to transfer to a protein substrate, which is sitting over here. So these are things that you have an opportunity to do when you have a very large family. And so what we've tried to do is put together a very diverse group of speakers here, and to keep this as a real workshop format, and to start out with some of the key structural biologists who've really contributed so much to this kinase field. And that will be our first session this morning. Stefan had a surgery last week and had some complications from that surgery, and so couldn't be here. And Ruben Abanya is going to speak in his place. They've actually been collaborating on a number of things. But Stefan will certainly keep in the loop, and I would like to keep those of you who are interested in really trying to find ways to follow through to see if we can really keep a follow-through mechanism for some of this. And then we're going to look in the afternoon at some of the more mechanistic questions. The evolution, what do we learn from the evolution of this family? What about the the kinetic mechanisms, and then also I think a new thing where we have NMR data that we're able to really look at the residue-specific dynamic changes in contrast to the crystal structures where you have a static structure. So I think that's a new dimension that's just opening up in the kinase field as well. And then we'll look at some other mechanisms for looking at families, looking at proteins in solution. And again, where are the opportunities here? And it's, I think, really important for us to be able to understand how these molecules work in solution, not just how they look in a static crystal structure, but how do they behave in solution. And so we're sort of combining some of the computational approaches here with some of the other solution methods. And then the last session really going into a lot of the molecular dynamics and, again, how we think about the dynamic features of these proteins. And sometimes it's a substrate that's disordered and only becomes ordered upon binding to the active site cleft, like PKI, but other times it's regions within the kinase, like the activation loop or the C-terminal tail, that are disordered, and they only become ordered when they are recruited to the active site cleft. So there are a lot of opportunities for thinking about the dynamic behavior of these molecules and segments of these kinases. And then on Sunday morning, we're going to have, we'll sort of rearrange this to be sort of a roundtable, and have David Shaw. David Shaw is going to talk about the new computational opportunities with some of the new computers that are really able to compute so fast that it really does bring some of these, it really brings the molecular dynamics of simulations into a range where you can really experimentally validate some of the computations. And then Andy is also going to talk, and I think this is where we have some really unique opportunities to see how can we take advantage of the things that have happened over the last couple of years. Give your receipts to Juniper. Juniper's in the back there. She's the one who's helped with all the arrangements. She has really done an amazing job of putting this together. She's done all of them. And now I also want to introduce Mary Mizell, who's sitting here in the front. Mary's going to be helping to write this up, and hopefully if we move forward with some proposals, she can also help with that. And so I think I'll leave you there, and Louise Johnson is our first speaker, and she's going to kick off the scientific part.